Hello everyone. Today we're going to talk about how to implement the multivariable Newton-Raphson method or MNR in MATLAB. So first of all, make your MATLAB clean by typing clear and CLC. And then next is to define your set of variables. So looking at the emission on the upper right, we have two variables x and y. So we have to define a symbolic variable named x and y. And then the next step is to define the functions that you're going to solve. Well, it's a system of equations or function. And how do we do that? Let's say you have a simple equation x is equal to y. All you have to do is move all the variables into one side and just replace your 0 with an f. So f is equal to x minus y. I mean, it's not really, it's not, you do not really do it this way where you replace 0 with an f, but it does its job. Alright, so I'm gonna do the same on to our system of equations. So f1 is equal to x cubed minus 5 times x squared plus 2 times x minus y plus 13. That's my f1. My f2 is x cubed plus x squared minus 14x minus y minus 19. And the next step is to construct a function column matrix, and it's as simple as just containing all of these functions f1 and f2 into a single column array. So f1 separating to a column by using a semicolon, and then f2. And next step is we do the same thing for the variables. So I'm gonna call that variable matrix var. Var is equal to all of the var is equal to the column matrix containing all of the variables that we have used. So x and then y. And now we're going to construct the Jacobian matrix. And the Jacobian matrix is defined as, not really defined, but Jacobian matrix has an element such that the element at the ith row and jth column of the matrix is equal to the partial derivative of the ith function with respect to the jth x variable. So let's implement that. So first, we construct a for loop iterating over all the rows of the Jacobian matrix. And remember that the row, in that row, the ones that changing is the f, the function. Remember, f sub I. So for I is equal to 1 until the size of the function matrix. And now we're going to iterate over the columns. And remember that when the column is changing, the x variable is changing. So for j is equal to 1 into the size of var. And and remember the formula? I'm gonna show it again. The j I of j variable is equal to the partial derivative of fi with respect to x sub j. And implementing in MATLAB is no different than the formula that you have seen. So j of I comma j is equal to the derivative of f sub I or f of I with respect to the jth x variable. And now let's run it first to see if to see our Jacobian matrix. There we go. And now the next step is to construct a correction factor matrix. Well, we don't really need to construct the correction factor matrix, but it makes our code cleaner. So looking back to the equations, The correction factor is simply the division of the function matrix over the Jacobian matrix. And there's a negative sign there, but we can put it out and just take into account the negative sign later. So going back to our MATLAB, we're gonna make a matrix. Well, not really matrix, but question vector matrix. Delta x is equal to delta x is your question factor. Is equal to the inverse of j. Remember, f over j is the same as j raised to negative 1 times f. So inverse of j times the function matrix. And our question factor matrix is a function of two variables, which is x and y. And uh we can we can make this delta x into a function by simply adding a parenthesis and then typing var. Well, you can do delta x which is a function of x and y. But since you already put your variables into a variable matrix, you can just type in var to make your code simpler. And, and now we're ready to make the we're going to implement the iterative step of the Newton-Raphson multivariable Newton-Raphson method. So let's say uh, I want to have 8 iterations. So let's make a for loop going from 1 into num iteration, and let's look back at the equation. So if you remember, or if you look at it, the iteration equation is expanded. It's x sub n plus 1 is equal to x sub n minus f sub n over j sub n, where f of n all over j of n is already defined by us as the correction factor. So let's implement that. Oh, I just forgot to mention about the initial values. You can assume initial values that we like. Say our x initial is equal to 10 and our y initial is equal to 10. In your case, the initial values may have to be calculated. Well, not really calculated, but must be reasonable enough, especially in some applications where you have some restrictions. For example, I said that let's say the equation is x plus y is equal to 2. Then, if you assume y to be equal to 1, then the most reasonable assumption for x should also equal to 1. This makes your iterative step converge closer to the actual value. So after we assume the initial values, we construct a initial value matrix. So var init is equal to x init semicolon y init. And then we now plug in our equation, our iteration equation to the for loop. So let's say that the new n, which is x sub n plus 1, is var underscore new is equal to var init minus the correction factor, which is a function of two variables. And remember, these two variables are your current variable values. So var init 1, comma, var init 2. And then uh, don't forget to make your initial value into the no, don't forget your current value into the initial value. Okay, after that, we're almost done. Well, we're actually done, but let's let's just do a VPA. A VPA just makes your answers into a decimal form with a lot of digits. Because sometimes symbolic, like anything related to symbolic, for example, you have a function that is symbolic. Sometimes MATLAB expresses them in the command window in like that they look bad. Yeah, they just look bad. So var new is equal to VPA, and then var new, and now you're done. So all you have to do is just run it. Oh, wait, 9:26. Did we miss something out? Hmm. Oh, whoops. See, I forgot. Yes, we're using delta x. I've been using c as a correction factor. I forgot that we defined this as delta x. Now if we run it, what? Wait, var init. Oh, I just realized. Let's just say z is equal to 1 into num iteration. Oh, there we go. And now we have our solution to the system of equations. Now, how do you know which one is x and y? It depends on the order of your variable matrices. So we define the order to start from x and then going to y. So you have to know the order of your initial variable matrix as well as your variable matrix. And yeah, that's the multivariable Newton-Raphson method. Uh, thank you.